Hey guys, and welcome to the full course on Introduction to Finite Element Analysis, your gateway to mastering one of the most powerful techniques in engineering analysis and problem solving. This is a certified course, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we are dedicated to offering advanced, industry-relevant engineering courses crafted by industry experts. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we will cover in this training video. In the first chapter, we will introduce you to the fundamentals of finite element analysis. You will learn about its purpose and significance in solving engineering problems, especially when analytical or experimental methods fall short. We will discuss the different types of analyses carried out in FEA, including linear, nonlinear, dynamic, and thermal simulations. This chapter will also cover the stages of solving FEA problems, from CAD modeling to results validation, along with key concepts like the equation of motion and stiffness matrix. In the second chapter, we will discuss the inputs needed to perform an FEA analysis. You will learn about geometry requirements, material properties, boundary conditions, and loading. We will also guide you through the basic process, including meshing, defining materials and sectional properties, solving equations, and interpreting results. In the third chapter, we will explore the best practices in FEA modeling and simulation. This chapter will focus on how to set up simulations that mimic real-world conditions, verify material properties, avoid stress singularities, and ensure convergence of results. These practices will help you achieve accurate and reliable simulations. In the fourth chapter, we will introduce you to the current trends and growth opportunities in FEA. We will discuss the increasing demand for FEA skills in industries like aerospace, automotive, construction, and consumer electronics. You will also learn about how advancements in cloud-based systems and faster solvers are revolutionizing the FEA landscape. In the fifth chapter, we will discuss the software tools used in FEA, including industry favorites like Abacus, ANSYS, and Hypermesh. You will gain insights into how these tools are utilized in various domains to solve real-world engineering challenges. In the sixth chapter, we will explore the work opportunities and industries for FEA engineers. You will discover how FEA is applied across sectors like automotive, aerospace, biomedical, and virtual engineering. This chapter also highlights the critical skills you need to excel in this field, such as strong theoretical knowledge, modeling expertise, and proficiency with an FEA software. Thank you for joining us. We are thrilled to have you on this learning journey. Make sure to subscribe to our channel for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with Introduction to Finite Element Analysis and unlock your potential in this exciting domain.
Welcome to this webinar, and today we are going to have a webinar on the topic of basic introduction to FEA. So in this, basically the main objective or main agenda of this will be to give you some brief idea of the FEA, like brief idea about the FEA, and this basically this webinar is divided into 3 sessions. So first session is Introduction to FEA, in which I'm going to cover Introduction to Finite Element Analysis, type of analysis which are carried out in the FEA, stages to perform any FEA problem, what input we need to perform that FEA problem, basic process summary, and then basic key concepts like equation of motion or stiffness matrix, how it gets formed, and how we can apply the stiffness matrix while doing the FEA calculations. And then I'm also going to share best practices for modeling or simulating your FEA. In section 2 is opportunities for FEA engineers. So there I'm going to discuss about current trends and growth opportunities for FEA engineers. Then what softwares you should learn in the FEA, or what are the current softwares in the market. I'll give you that information. Then what are the work opportunities and industries in which we are widely using the FEA nowadays. And then I'll also share some critical skills required to get into this domain, so that when you come here, or when you start exploring this field, you will come with some background or some basic prerequisites. And then the last will be the question answer session. As over there, if you have any doubt, you can just drop it into the chat box, and then at the end of the seminar, I'll try to address those queries. So this is how our basic webinar is going to look today. And main objective of this webinar is to provide the basic overview process of the FEA. So when you complete this webinar, you will have some idea about the FEA process, what is FEA and how we carried out that. Then basic key concepts of the FEA. So if you start studying the FEA, this will definitely help you. Then provide the opportunities, information about the opportunities for FEA engineers, and then critical skills required to succeed in the as a FEA engineer. So all this, my main objective is to provide you all these insights, so that you will have some good learning about the FEA today. So let's begin with our section 1, that is introduction to FEA. Okay, in first section, first of all, I want to basically tell you that why we need FEA, why we need FEA. So in engineering problem, or as a mechanical engineer, our duty, or when we are into core mechanical thing, our main objective is to design the component, to design the equipment, so that it can sustain under given load conditions without occurring any kind of failure. Or if there is a failure, we should be aware that how much load it will take before it will actually fail. So that information we can get, when we want to have that information, we can get that information by using solution using either strength of material or theory of elasticity, are normally accomplished for the regions and loadings with relatively simple geometry. We can get that information from the strength of material, but that is very relatively, we can use that for very simple applications, because that is a formula based, and we have that is a basically simple geometry. We can say those formulas are applicable basically. So when in many applications involve cases with complex shapes and boundary conditions and material behavior, therefore we can say that in theoretically we can solve simple problem, but practically when we come in the practical component design world, we have the different scenarios, different complex component is there, complex geometries are there, the complex boundary conditions and loading conditions are there, and we want to predict the results for all these different scenarios. And at that time it is kind of difficult, or let's say not kind of difficult, or we can say impossible to do it with the when we use the analytical method. And therefore we can say that the gap exists between what is needed in the applications and what can be solved by analytical closed form methods. So, and this gap actually leads to the development of several numerical methods. And finite element method, or finite element analysis, is one of the numerical method. So here is a brief introduction of why we need FEA, or what is the need of FEA basically. To summarize, we can say that to solve any engineering problem, there are three types of methods. So first is analytical method, second one is numerical method, and third one is experimental method. And each of this method has its own positives and negatives. So if you go with the analytical method is a classical approach where we are using the closed form equation to solve any kind of problem, and where you know the error is zero because you are 100% accurate. So you have the geometry, you have the formulas, and you are just solving it. So that is 100% accurate, but that is only valid for simple geometries, because for complex geometries you cannot do those complex calculations by hand. Second method is numerical method. So in this numerical methods, what we do is it's a mathematical representation of physical problem. Then it's a approximate assumptions mode. It is applicable even if physical prototype is not available. So when we say it is approximate assumptions mode, it means that there are assumptions which we take into the considerations like material or boundary conditions, but those assumptions are very close to the real life problems. So in that case, though we have some assumptions, but still we can trust those results. Then it applicable if physical prototype is not available, we can have the CAD model and we can solve that. We don't need any physical prototype for that. Then solve real life complicated problems, and any kind of scenario actually we can simulate with the numerical method, but the results cannot blindly trusted. We must verify with the experimental method or with the hand calculations for the validation. So we can say it has very wide scope, but we also cannot blindly trust it, but we can get the solutions for a lot of problems by using numerical method. Then the third method is experimental method. In experimental method is an actual measurement method which we do in the lab. Then but it is very time consuming and it needs actual setup. It needs lot of prototypes. We need at least 3 to 5 prototypes we have to test before we actually say the results are looking good or results are trustworthy. We have to at least go for 3 to 5 prototypes, and it involves a lot of cost also as well as time. And basically the biggest disadvantage I can say for the experimental method, only experimental method, if we trust that we need lot of, if we want to go with lot of design iterations, then it takes a lot of time to complete that prototype, and which involves cost as well as time. So experimental method is there, but it is very time consuming. So if we compare all these 3 methods, so out of that numerical method is one of the best method which we are using nowadays to solve any engineering, mechanical engineering problem. Then what are the different numerical methods we are having nowadays? So we are having finite element method, boundary element method, finite volume method, and finite difference method. In finite element method, we find the approximate solutions to the boundary volume problems for partial differential equations. We actually here try to solve the partial differential equations in finite element analysis. Then in boundary element method, we analysis is done on the only on the outer surface of the body. Then in the finite volume method, it is more mainly suitable for computational fluid dynamics. And finite difference method is in that method we solve the differential equations, not the partial differential equations. So if we compare these 4 method, we can say that in boundary element method we are just solving it for the outer domain. So what is happening inside the body we don't have the visibility by using the boundary element method. So over there we get the restriction for that method. Finite volume method is mainly used for the computational fluid dynamics. So if you have the structural problems, you cannot go with that method. Then finite difference method, here you actually solve the differential equations, and it is very difficult to solve the differential equation for complex geometry. For simple geometry you can do that, but for complex geometry it is really difficult. So the finite element method, which is basically depend on the solving the partial differential equation, is the best method out of all these four, which can give you most accurate results. So and that's why finite element method is so widely we are using in the industry. So for fluid dynamics problem, we use the FVM, that is finite volume method, and for structural related problems, for thermal related problem, we go with the finite element method, as those are the methods which will give you the best results for any mechanical problem. Then now let's dig more into what is finite element analysis. So the finite element analysis is a numerical method for solving a problem of engineering and mathematical physics. For given structure, the behavior of the structure can be described by governing differential equations. To approximately predict the behavior of the structure, it is necessary to find a solution of governing differential equations. So basically, finite element method is based on the discretization of the actual domain. So what we can summarize in a simple term is that in a problem domain is a collection of subdomains. Like if we have the big component or big domain, we are going to divide that or discretize that into number of subdomains called elements. We are going to solve the problem at each subdomain, then assemble element to find out the global solution, then assemble those equations, elemental level equations, to find the global solution. Solution is guaranteed to converge to the correct solution if proper theory, element formulation, and solution procedure are followed. So this is basically FEA that we have for continuous problem. We have a number of particles. We have a number of particles like infinite degrees of freedom, we can say. It is not possible to solve those infinite number of solutions. So what we do with the discretization, we are cutting the geometry into number of pieces. We are trying to solve those for that subdomain. We assemble those subdomain together to define the entire geometry, and then we solve the unknown basically, which we need from the simulation. Advantages of FEA analysis is predict product performance. Basically, how is for the given load, how your product is going to perform, how the stresses are looking, how the strain is, how the displacement is. So basically validate your design, reduce the raw material. If you find the stresses are very low for the given material, we can definitely play with the thickness or other parameters so that we can cut down on the material and we can save the cost over there. Ensure optimal design, best possible design. By using the FEA, we can give the optimal design. Then we can use this method for verification purpose. It reduces manual testing and prototyping time because it is cut down on number of iterations, design iterations, which you will actually need to build the prototype. So over there, you're saving a lot of time and cost, and you're giving the quick solution by using this method. This what if scenario. So you can study different type of scenarios by using the finite element analysis method, and you can foolproof your design by applying those different scenarios and seeing the results for those scenarios, and validate your component is going to sustain for those particular scenarios also. And it shortened the design time. Absolutely, it shortened the design time, no doubt about it. So these are the advantages, and they are very promising advantages. And because of that, we can save a lot of time, a lot of cost, and a lot of efforts also. So no, definitely, and that's why nowadays we are using finite element analysis method so widely in the industry. Then type of analysis which we carried out are generally linear analysis, nonlinear analysis, dynamic analysis, buckling analysis, thermal analysis, fatigue analysis, crash analysis, and NVH analysis. So I would like to give a brief summary about each of this. So in linear static analysis, basically what we consider is that our load, whatever we are applying, is constant throughout the time. It is not varying with respect to time. Force versus displacement, if you plot force versus displacement, it has a linear curve, linear graph for force versus displacement, has a linear relation between them. uh, what does it mean is like if for 1 Newton force, if you're getting 2 mm displacement, then for 2 Newton force you are going to get 4 mm displacement. That is a linearly related force versus displacement ratio. Then we can assume that it has all the linear properties, like it has material properties which are constant throughout the simulation. Its geometry is not changing. Its geometry is not changing, and it is not going under any nonlinearity in this simulation. So it is kind of very simple analysis, which we assume it is very easy to solve basically for the software. And over here, we can also apply the superposition method, and the results can be scalable actually. So the results can be scalable, and superposition method we can apply over here. So this is basically linear static analysis, but it is only valid for where you have the constant material properties, and where you have the not complex contacts are there, no non-linearity is present basically over there. For that kind of scenario, linear analysis or linear static analysis, we can say, is very helpful. Then for nonlinear analysis is the analysis in which basically the we can say that load is constant, but load what we are applying is incremental in the software. Then we can say that force versus displacement ratio is not linear in this case. It is non-linear. We are going under, geometry is going under large deformation. So because it is going under large deformation, we have to consider the geometrical non-linearities. The changing shape of the geometry, we have to consider that when we are doing the FEA. Then here we also consider the nonlinear material properties. We can say that we have to specify the material behavior after once it crosses the yield point. What is the behavior? That behavior we have to define when we are saying mm, nonlinear material properties in the material. Like we have to specify the. I will come to that, but it like plastic strain and yield strength we have to specify for nonlinear material proper nonlinear analysis. And then over here we also consider the boundary nonlinearity. Means if the components are changing their contacts, we are considering all those effects into this analysis. So in this analysis, you can find out a lot of convergence issues and a lot of skill required to perform nonlinear simulation. Then dynamic simulation is basically where load is going to vary with respect to time. And here the type of simulations we performed is modal simulation, frequency response simulation, and basically we also study in different type of vibrations in dynamic analysis. Then buckling analysis is one. Thermal analysis, where we want to find out the stresses occurred in the component when the temperature is changing. So what are the effect of the temperature changes on the stresses? That study we do using the thermal analysis. Then basically thermal analysis is useful for core engine components. It is very, very useful analysis. Then for large data centers enclosures, I must say thermal analysis is a very, very important analysis. Then fatigue analysis is generally for to find out the life cycle. For rotating components, fatigue analysis is very useful. Then crash analysis for car collision. Generally, we go for crash analysis, then NVH analysis. So, and there are many more, but these are the most popular and most used analysis which we do in the FEA. Then now, as we have little bit idea about why we do FEA or what is FEA, I'm going to go more details that stages of FEA. So there are basically, I say, 4 stages of FEA. Like we need a CAD model to build the FEA. We have to do the pre-processing. We are going to solve the solution and then the post processing. These are the 4 main stages to perform any FEA simulation. So CAD data we have to take from the CAD department. Then pre-processing is the one. CAD data is like geometry. We are having our geometry to perform the FEA. Then in pre-processing, first step is that discretization. That is a meshing. We have to divide that domain into number of subdomains so that we can define our problem more properly. So that's why and we can solve our partial differential equations. And that's why discretization is very important step in the in the FEA pre-processing. Then apply the boundary conditions. Before applying the boundary conditions, you have to specify the properties, like so what are the sectional properties for this component, what are the material properties, you have to define them. Then you will go for the boundary conditions and loading, and then solution, what type of solution you want. That is, there you have to specify the load step, and you have to specify the step basically, where you will define what type of analysis I want to do, and what will be the output I'm interested in. All that data you will provide over there. Then after that we will go for the solution, where software will actually run the program at the back end and try to solve all those partial differential equations and give you the result for entire domain in the form of displacement, stresses, and strain. Then in the post processing, we are going to review the results, validate the results, and if we are finding the stresses are too high, or we are not the results are not satisfactorily, and we have to do some design changes, then again you will go back to the CAD cycle, and again you have to go for the CAD modification, again pre-processing. So this cycle keeps repeating unless and until you find the correct solution. Then in input needed to perform FEA. So here I'm going to tell you more in detail about geometry. That is, what we need is a 3D CAD model. In the sectional properties, I will need for the 1D beam element, I'm going to, for 1D element like beam element, bar element, trusses element, spring element, what I will need is their sectional properties to define the component, or to define that in a complete manner, so that I can do the calculations on that. If I'm having the beam 1D beam element, so for that I will need the area as a sectional property. Sometime moment of inertia, I will need to define that element. For spring I will need the spring stiffness. Then for 2D element I will need the thickness, because I'm having the surface, but I will need the thickness to define that geometry completely into the FEA domain, so that it will do the calculations which I need. For 3D element, you don't need to do any sectional properties, because 3D element it's completely defining the geometry. So for that you don't need any kind of sectional properties. But after the geometry you will need these sectional properties, and these sectional properties you can take from the CAD, and it is always good to verify that with your CAD department, and understand what your considerations are correct or not. Then the third one is material. In the material, for linear analysis, we have to use the Young's modulus and Poisson's ratio. These are the 2 main material properties. Basically, when we give these 2 material properties, other properties it will calculate automatically based on the other equations and relations, we can find out other properties. But basic need is Young's modulus and Poisson's ratio. Then nonlinear analysis, we have to Young's modulus, Poisson's ratio, yield stress, and plastic strain we have to define. For the dynamic analysis, you will need, along with the Young's modulus and Poisson's ratio, you will also need the density, because in dynamic analysis you are also going to consider the effect of inertia, and for that density is important. So we have to specify the density when we are going for dynamic analysis. And then the thermal analysis, basic is coefficient of thermal expansion, and for the boundary conditions you will specify the temperatures. Now, when we say we will need the load also, once you do the first three steps, after that you have to define what load is going to apply on the structure. Then for that load, we can say that structural loads are forces applied to the part or assembly during the operation. Such loads cause stresses, deformation, and displacement in the component. So we have to basically study with that applied load what are the stresses, deformation, and strain coming in the component, in the given component, basically. And the type of loads can be inertial load, structural supports, and thermal load. These are the loads which we have to specify. Then boundary conditions are also very important, and the test data. The boundary conditions are the most important, actually, the thing in this, because if we miss to give the boundary conditions, we can end it with a lot of numerical errors while solving the simulation. Basically, when we solve the linear and nonlinear static simulation, at that time you will end up with a lot of errors if you miss to give the boundary conditions. In the boundary conditions, we are basically defining this type of supports now which object will have. It can be a fixed support, it can be a support constraint, it can be a pinned support, or roller support. But we have to define whatever is the support, we have to define that support, and apply the load, so that in that way we are actually simulating that actual behavior of the case. Then we will need the test data. It is always good to have test data for validation purpose, because when you will get your FEA results, it's always good to cross check with the test data, so that you will be assured that whatever calculations you are doing are correct, or whatever assumptions you have considered are correct. And here also we say that with the test data or with the hand calculation, there can be plus minus 10% error is acceptable, but mm, but it is always good to have less error than that. So these are the basic input requirement for the FEA. Then I'll go with the basic process summary for the FEA. So in that, now this is kind of technical. So in that, first step is that domain discretization. That is what we are doing as a meshing. Then select the element type. Here we are defining the shape function, and we are defining how that element is going to behave, or what type of behavior that element is going to capture by selecting the type of element. Then we are defining the geometry as well as the behavior, actually, by selecting the element. Then we are deriving the element equations. The third step is deriving the element equation. Fourth step is assemble those element equation in the form of global system. So in this, we are, after that we are going to solve this stiffness matrix, like this equation. We can say this is the equation for static analysis, like Ku is equal to F is the static analysis equation which we solve at the back end. So K is nothing but the stiffness property of the matrix. U is the nodal displacement vector. F is the nodal force vector. The fifth step will be incorporate boundary and initial condition. That will be our fifth step. Then solve the assembled equations, solve the system of equation for unknown nodal, and then the displacement, First of all, we will solve it for the nodal displacement, and then we are go from the nodal displacement. We will go with the strain, and from the stress-strain relationship, we will find out for the stress. So that will be our sequence actually in the backend. So the logic behind FEA is this: why, how the actually software will solve this equation is this is the summary form. So I also want to tell you in brief that when I say, I want to tell you the steps, like again, in another words, like first step will be the discretization. Second step will be the defining the global displacement vector U. Then define the element properties and material properties. Fourth will be compute the element stiffness matrix. Fifth will be compute the singular global stiffness matrix. Sixth point will be define the boundary conditions to remove all free body motions, because when we will have the stiffness matrix, it will be without boundary condition. So what does it mean? That it will have the rigid body motion, that you don't have any constraint. So when we are applying the load, the body will move as a rigid body motion with rigid body without any deformation or without any strain. So and in that case, the software cannot solve that equation. Then compute the non-singular global stiffness matrix, then define the external load and compute it, solve the static equilibrium equations, compute the displacement vector, and after that compute the other outputs like stress and strain and contact pressure and all other things. You can definitely go ahead and use that. Then here I want to explain you that basically what is stiffness matrix. When we go for the stiffness matrix, what is stiffness matrix or how that stiffness matrix is going to solve your equation. So let's consider this is a spring. The stiffness matrix constrain the geometry and material behavior information that indicate the resistance of the element to deformation when subjected to the loading. So if I how we form the stiffness matrix, here I want to explain you that. So consider this is a spring. It has the point 1 and 2. We can consider that as a node 1 and node 2. These two nodes we are going to attach with the spring. This is our element basically, which has the two nodes. Then we are applying the force F1 at node 1. We are applying the force F2 at node 2. Because of force 1, we are getting the U1 displacement, and because the force 2, we are getting the U2 displacement. So if we solve the equilibrium at node 1, the equation what we will get is F1 is equal to KU1 minus KU2. And at node 2, the equation we will get is F2 is equal to minus KU1 plus KU2. If we go ahead and form the matrix with these equilibrium equations, we can also write in the matrix form for easy solution. So we are going to write in the matrix form. So in that case, we will have the K as a stiffness matrix. We will have the displacement matrix. We will have the force vectors, nodal force vector. So the matrix will look like K minus Ku minus Ku K, then U1 U2 is equal to F1 and F2. This will form Ku is equal to F is the equation basically, or is the matrix which we are going to solve for the linear analysis. Basically, this equation is only valid for static analysis, not linear, but static analysis, like linear as well as non-linear static analysis. This is the equation. But the difference here is that for linear analysis, the stiffness is going to be constant throughout the simulation, and for non-linear analysis, the stiffness is going to change continuously. And for that, you have to, if, with every increment, you have to solve the stiffness matrix for nonlinear simulation. Then For stiffness matrix, I want to give you more information, like how we arrive with our stiffness matrix, or what is this stiffness matrix means for. So we know that deflection or displacement is equal to PL upon AE, that is force into length divided by area into Young's modulus. Then if we also know that K is nothing but force required to produce unit displacement. So if we write P divided by D, what we will get is that AE by L. So this AE by L, we are going to put in this stiffness matrix basically. Instead of K, we are going to write AE into L, because when we are having the FEA, we know the material properties and we know the geometry, and through which we are going to define the stiffness matrix over there. And displacement is unknown. Forces we know, F1 and F2, and we know the stiffness matrix. So we will invert the stiffness matrix over here to find the U1 and U2. We will invert the stiffness matrix. We will create the equation. We will solve for unknown U1 and unknown U2. So what are the properties of the stiffness matrix? Stiffness matrix is symmetric. What does it mean? This is consequence of the symmetry of the forces, like equal and opposite, to ensure the equilibrium. And that's why we can say that stiffness matrix is symmetric. If you say the stiffness matrix is symmetric, 1, minus 1, minus 1, and 1, the stiffness matrix is symmetric diagonally, then matrix is singular. It means that when you find the determinant of that matrix, you will get as a 0, and you cannot solve that, and therefore not invertible. You cannot solve it. That is because the problem as defined is incomplete and does not have the solution. No constraints are applied to prevent the rigid body motion to the system. Hence, boundary conditions are required. So that is why we need the boundary condition to avoid any kind of non-singularity. To have the non-singular matrix, it is important to apply the boundary conditions. Then system matrix is simply a superposition of individual element stiffness matrix with the proper assignment of element nodal displacements and associated stiffness coefficient to system nodal displacement. These are the properties of the stiffness matrix. Then we are going ahead, and I want to share the most important terms in the FEA, that is nodes and elements. So what are the nodes? So here we can say this is a node. Node is a coordinate location in a space where the degree of freedom and physical properties like stress, temperature, velocity, etc. are defined. What does this mean? Is that node is a location basically where we are applying the where it will have the degrees of freedom. What is my degrees of freedom? It means that if you have the any point, you need some coordinates or xy system to define that point in a space. So for the point for the point, you will have the two degrees of freedom, that is x and y. If you consider a line, you will have x and y coordinate. Along with that, you have to also specify what is the angle for the for that line. So that is what the degree of freedom means. How many parameters you will need to define the body completely into space is nothing but the degrees of freedom, and our calculations we can do at those nodal points. And basically displacement we find at the nodal points, and sequentially stresses and strain also we are found always at the node location. And then what is the element? An element is a mathematical entity that defines how the shape and physical property of an internal point is interpolated from the node positions and physical properties. What does this mean is that basically numerical method is a discretization method of a continuous domain. Okay, so that your computer will understand that language. Then the result of this discretization mesh is composed of node located in the space connected with the entities called elements. So results of the discretization is nothing but a mesh. What we get is a mesh which is composed of nodes located in a space, and those nodes we are connecting with the entity called elements. So basically we are connecting two nodes, 2 points with the entity. That entity is nothing but the element. Then the calculations are basically done at the node and interpolated through the element. So we are going to do all the calculation mostly at the node location, and then the results will get interpolated for that particular element. But whenever you are addressing any displacement or stress, we always review the nodal results. Therefore, accuracy of the results is depending on the number of nodes used to discretize the system. Because more number of nodes, more accurately you are going to capture the geometry and more accurate results you are going to have. Then these are the different type of elements like line element, 2D element and 3D elements. Uh, so line elements are nothing but the 1D elements like beam element, spring element. 2D elements are the planar elements. And the 3D elements are the planar elements that are triangular or quadrilateral with a specific thickness. And the brick element. 3D plate element are like that, 3D shell element, and 3D brick element like enclosed 3D volume with 4, 5, 6, or 8 corner nodes. So these are we can say different type of elements. This is line element, 1D element, and this is 2D tria element. This is 2D quad element. This is 3D tetra element. Then we have this is a linear, and this is we can say quadratic or parabolic. So here we have the again only the it's like we will have extra nodes on this, like extra computation points where we are going to do the calculation. So accuracy of these elements like will be higher as compared to the linear element. Quadrilateral elements will always have higher accuracy. So and this is the example of that. And here we can say this is a penta element, 3D penta element. This is 3D quad element basically, or hex element. Then this is the example of the mesh component. So let's say this is a part, and what we are doing, we are meshing the component. It means you are dividing the geometry with these, whatever you're saying in the gray lined, these are the elements basically, and the point which is connecting those elements are nothing but the node over here. So this is how our 3D mesh model will look. Then what best practices we do is like set up simulation to match real world problem. Basically best practices is that set up the simulation in such a way that you will capture the real life scenario as much as possible. Then verify the material properties. It is important because your accuracy of the results is depend on material properties, your geometry, your sectional properties, whatever you are considering. On that only your accuracy of the FEA is depend. So it is important to verify the material properties. Use engineering knowledge and judgment. Then avoid putting load on nodes or small edges, because if we put the load on the small edge, you will end up with the stress singularity error. Then and that will be unrealistic stress which we are getting, because you are applying the load at only one location, and you will end up not capturing the actual behavior. Then choose formulation type like linear or non-linear. That is linear element or no, linear element or quadrilateral element. That is the meaning of that. Quadrilateral elements will give the good results, but that is also, it's also depend on analysis to analysis. Then identify the stress singularities. Ensure your results converge properly. 100% your results is going to converge. That you have to uh, understand. So these are the best practices which you generally do while you are doing the FEA. Now we are going with the section 2. Here I'm going to share the current trends and opportunities for the FEA. So I want to tell you that for the here we can say that what was market share for 2019, how it was looking. So for finite element analysis segment is dominated in 2019, and this is because of the cloud-based system. Because now we have the large storage system, we have the faster solvers to solve, and that's why our efficiency is increasing, and we can do more and more FEA work. The automotive segments held the dominant share in 2019, uh, mm, and then the aerospace sector is expected to witness the high growth rate over the forecast period. The aerospace sector, yeah, because that is one of the booming sector in which we are using the FEA nowadays a lot. Then Asia Pacific and South Asia, America are poised to emerge as a lucrative region markets for CA softwares over the forecast period. So I must say that these are the regions where Asia or South America, these are the regions where FEA is going to use very widely in near future. Then key players in the market, which includes Siemens, EXA Corporation, MSC Software Corporation, and ESI Group, which is from France. So these are the key players, but there are so many players in the industry present. So these are the current trends. So from here we can conclude that FEA in near future, FEA is having a lot of bright future. If anybody want to pursue the career in the field of FEA, it is the right time. Then current trends and opportunities for FEA. In this, we are next. We are going to see what are the softwares which are in the market. So these are the softwares like we are mostly using nowadays: Abacus, Standard, and Explicit, ANSYS, Hypermesh, SolidWorks, Nastran, ANSA, LSDyna, MATLAB, NX Ideas, Fluent, OptiStruct, Patran, ProMechanica, Radios, Unigraphics. So these are the softwares which are basically most widely getting used in the field of FEA nowadays to, uh, to solve any problem. Then work opportunities and industries. So FEA is basically everywhere. In all industries nowadays, we are using FEA to get more trustworthy results. So we can say aerospace industry, automotive, off-highway construction, medical devices, consumer electronics, civil engineering, electrical engineering, biomedical, and virtual engineering. For virtual engineering, nowadays Facebook is a very emerging partner for the they are doing a lot of virtual engineering work nowadays. Uh, and then electronic consumer electronics like companies like Microsoft, Amazon, they are there. Aerospace, Boeing is there, and many other Airbus and many other components are there. Many other companies are there. For automotive, we can say Chrysler, Caterpillar, Chrysler, Cummins, they are all there for automotive and engines basically. Then off-highway construction equipments, Caterpillar is there, and like that, it has lot of scope. And as people are getting more and more aware about it, this technology is getting very famous. uh, then if you want to like learn the FEA, what skills or what stages you should take. So FEA learning process is like stage 1, stage 2, stage 3. Stage 1 will be learning FEA theory. So this is like a very basic introduction which I am giving right now, but FEA is a very vast subject. So learning FEA theory is very important. So in that case, you have to understand exactly what are the nodes, what are the elements, what are the partial differential equations, what are the integration points, what are the shape functions, how we are calculating different theories, and what is the logic behind it, how we formulate the stiffness matrices for complex mm, complex problems. So all those things you have to study. So it is good to go with the basic theoretical knowledge about the FEA. Then second point, you have to be good with the modeling practice, learning proper modeling practice. Like based on the shape of the geometry, you should able to decide what type of elements you are going to use, how your geometry will be, then what type of behavior you want to capture for that, what type of elements you are going to use, and all that, how different type of connections you are going to define, how you are going to simulate your entire complex model or complex assemblies, that you should be very have good knowledge about. Or if you want to do the meshing, how you can control the number of nodes or number of elements by but you also give the high quality. So all that judgment you have to have good knowledge about. Then learning how to use the FEA software is the part. But how to use the FEA software you can learn eventually once you get into the FEA, but having the good theoretical knowledge about the FEA and good modeling techniques, knowledge of good modeling techniques is like a very important skills which you should have. And then apart from that, you should be good or have basic fundamental knowledge about statics, mechanics of material, dynamics, machine design, and engineering graphics to succeed in this field. So I must say that if you can learn on all this or get some basic idea, you can definitely get into FEA and be successful in this field.